Something is leaking in the dark between worlds. A Manhattan-sized object designated 3I/ has entered our solar system, but it isn't behaving like a comet. The James Webb Space Telescope has captured evidence of a metal-rich jet not trailing away from the sun, but firing directly toward it. This isn't just random debris. It's chemistry we've only ever seen in factories. Now, astronomers are asking the unthinkable. Is this the first sign of interstellar machinery drifting silently through our cosmic neighborhood? The arrival of the stranger began in early July 2025, when a telescope in Chile made a discovery that instantly joined a very short list. The object was labeled 3I/A, the third known interstellar visitor ever recorded after Oumuamua in 2017 and 2I/Borisov in 2019. The I stood for its interstellar nature, confirming this body was not born in our solar system. It was on a hyperbolic trajectory, flying through at nearly 47 kilometers per second, completely untethered to the sun's gravity. Astronomers initially classified it as a comet, but within days, its behavior began to contradict everything we thought we understood about how such objects behave. The first clues came through its orbit and speed. Using trajectory models and spectral data, researchers traced its likely origin to the Milky Way's thick disk, a part of our galaxy known for older, high-velocity stars and debris. As 3I/A approached the inner system between Mars and the Sun, it offered a rare chance for high-resolution observation. Expectations were clear. It would warm, emit gases, and produce a glowing tail. But it didn't. Instead, telescopes found no sweeping dust plume, just a dark, silent object emitting matter in a strangely focused way. By July 1st, Hubble's observations revealed something unsettling. Rather than a tail streaming away from the sun, 3I/A was ejecting a dense, targeted jet of material toward it. This wasn't a tail. It was a thrust. The material expelled wasn't light ice or vapor either. It included carbon dioxide, trace cyanide, and an unusually high concentration of nickel without iron, which should always accompany it. This was no ordinary comet. Even before James Webb trained its instruments, the data whispered something that scientists rarely entertain. A natural law was being quietly rewritten. But if the arrival shocked scientists, the behavior that followed defied centuries of cometary physics and pointed to something far more deliberate. The conflict between expectation and reality became stark. Comets are supposed to be predictable. They approach the sun, warm up, and eject gas and dust in a dramatic tail that always points away from the heat. It's a simple dance. Sublimation, solar wind, and radiation pressure produce that iconic glowing veil. This is not theory. It's been observed in hundreds of cases. Even the previous two interstellar visitors, Oumuamua and 2I/Borisov, followed this pattern. So when 3I/ failed to perform on cue, the alarm bells began ringing across observatories. Instead of a curved tail, telescopes like Hubble and Gemini South saw a hard, sunward-pointed jet. In late July 2025, imaging showed a narrow stream of expelled material arcing directly at the sun. This jet wasn't light and dusty. It was dense, ejecting roughly 150 kilograms per second of matter. And it wasn't diffuse. It was tight, focused, and according to some, nearly collimated. That word collimated belongs more to rocket science than to comet studies. But it fits because 3I/A seemed to be directing its emissions, not bleeding them out randomly. Adding to the mystery was how consistent the plume appeared. Instruments picked up pulsing behavior, possibly linked to a rotation period or timed venting. That kind of modulation implies gating, a term borrowed from engineering where flow is managed precisely. Natural processes like this aren't unheard of, but this was precise and periodic, more like a machine than a melting rock. If this were just odd chemistry, it might still fit within extreme comet behavior. But this wasn't just chemistry. It was geometry, the directionality, the precision, the absence of expected structures, all combined into a message that the universe rarely sends. This object wasn't cooperating with physics as we know it. What truly shattered expectations, though, wasn't the shape of the jet, but what it was made of. A chemical composition emerged that pointed to something even stranger than motion. The composition provided profound clues. Every comet ever observed contains a familiar blend of elements: water, carbon dioxide, dust, iron, and nickel. These are siblings forged in the hearts of stars. Iron and nickel always travel together, born from the same supernova and locked in elemental companionship. But when researchers analyzed the spectra of 3I/ in August 2025 using the Keck 2 telescope in Hawaii, they saw something that had never appeared before. Nickel was present at about 4 grams per second, but iron was missing. That absence broke a rule as old as star formation. The material being expelled wasn't just metal. It was a compound, nickel tetracarbonyl. On Earth, this molecule exists only in controlled industrial environments. It forms when nickel reacts with carbon monoxide under high pressure and moderate temperatures, conditions that don't naturally occur on comets. This compound is toxic, volatile, and used in aerospace, plating, and metallurgical reinforcement. Its presence on an interstellar object immediately drew scrutiny from experts like Harvard astrophysicist Avi Loeb, who publicly stated that it resembled industrial emissions more than comet exhaust. Worse still, this wasn't a spike or a fluke. The readings were consistent across multiple instruments and confirmed by the James Webb Space Telescope's NIR-SPEC instrument in early September. There was no accompanying dust tail, no typical silicate emissions, and no scattered light to obscure the signal. This wasn't a comet shedding ice. It was something venting engineered compounds in a controlled and steady stream. The chemical message was becoming hard to ignore. Where there should have been randomness, there was order. Where there should have been iron, there was silence. And where there should have been nature, there was a molecule whispering of industry. But even if chemistry could somehow be explained, the jet's behavior pointed to something far more provocative. A comet that seemed to act not just unusually, but purposefully. The behavior spoke of control. Standard comet jets are messy affairs. They boil off randomly from sunlit surfaces, scatter chaotically, and obey the sun's push like smoke in the wind. But not this one. In late July 2025, the Hubble Space Telescope captured an image of 3I/A that left researchers stunned. A focused, directional jet was streaming toward the sun, not away. It carried about 330 pounds per second of material, including CO2, trace cyanide, and that same nickel compound, but again, no iron. More strangely, the jet was dense, linear, and unnaturally narrow. This wasn't just odd, it was wrong. Solar radiation pressure should blow such material backward, forming a tail opposite the sun. But here, the jet was resisting that force. For it to maintain direction, it would require thrust or some form of internal collimation. That suggests mechanisms, either channels, nozzles, or internal cavities regulating flow. Natural vents don't focus like that. To resist the solar wind, a body must be emitting with enough force to overcome that pressure, akin to firing a thruster. Then came the pulse. Data from Keck 2 showed variation over time, a periodic rhythm to the outgassing. Rather than a steady leak, it surged and faded like a heartbeat, implying not randomness, but timing. Scientists describe this as modulated emission, something more like software than geology. In engineering, this is called gating, the timed release of flow based on internal cycles or feedback loops. And so, a picture emerged. Not a leaking rock, but a system. Not a frozen wanderer, but an active participant in its own transformation, shaping how and when it interacts with the environment around it. With every expelled gram of nickel and each pulse of mass, 3I/ seemed to be rewriting its own surface, recasting itself not as debris, but as something that endures. Observations of its surface and reflection revealed more. As 3I/A moved closer to the sun between August and October 2025, astronomers noticed something unexpected. Its brightness increased dramatically. This is not unusual for a warming comet. Except the increase didn't stop even as the object began to recede from the sun. The light curve, normally peaking near perihelion, kept rising. Something was changing on the object's surface, and it wasn't dust. Spectral analysis showed no sign of typical silicates or ice crystals. Instead, reflection increased sharply in the near-infrared, consistent with metal. The most plausible explanation was that the object was plating itself. The nickel tetracarbonyl compound emitted in the jet decomposes under sunlight into pure nickel and carbon dioxide. That pure nickel could recondense onto the surface, forming a thin metallic layer. On Earth, this is called chemical vapor deposition, a process used in factories to coat components with precision metals. In space, this would create a mirror, and that mirror would serve a vital function: thermal protection. A more reflective surface would bounce solar radiation back, lowering surface temperature. This is known in engineering as passive thermal regulation, used in spacecraft to prevent overheating. It explains how 3I/ survived its solar approach with no catastrophic loss. The more it reflected, the more it cooled. And the more it cooled, the longer it endured. In September, observatories reported a steady increase in albedo, not tied to distance, but to surface transformation. The comet wasn't burning up. It was evolving. By using its own exhaust to shield itself, it had turned a death spiral into a survival loop. It wasn't melting under pressure. It was adapting. Its orbit and dynamics told a similar story of anomaly. By October 2025, as 3I/A passed within 12 million miles of Mars, something peculiar emerged, not from its chemistry this time, but from its path. Calculations from NASA's Jet Propulsion Laboratory and the Minor Planet Center began showing tiny but consistent deviations in its predicted orbit. These changes were on the order of microarc seconds, minuscule shifts, but always in the same direction. Comets can drift slightly due to uneven gas jets, but this was different. The direction of deviation aligned with the jet pointed toward the sun. This suggested internal torque or propulsion, not the kind that tears a comet apart, but the kind that steadies it. In fact, 3I/A exhibited remarkable stability. Most comets tumble chaotically. Their mass loss is erratic. But here the spin rate remained constant. It wasn't wobbling. It was turning deliberately like a spacecraft, orienting for balance. This pointed to a deeper level of control, something regulating its angular momentum as it moved through the inner